I need to conduct one more class, okay, and then I'll be able to complete what I wanted to complete. So yeah, so and next week I have a very busy schedule because there are some project presentations, project viva, comprehensive viva in our department, and I have to be available throughout the day. I mean, in different times. So I'm not very sure whether I'll be able to conduct the class next week on Thursday. But hopefully I'll be able to conduct the class next week on Friday, and that will be the end of this course. I mean, I hope that I'll be able to finish what I wanted to discuss with you, and yeah. So I'll let you know basically like in next week when I shall conduct the lecture. Okay, so I plan to finish by today itself, but somehow I could not manage it. Anyway, so last day what we discussed, yesterday what we discussed, it's basically this is what is called the Schmidt decomposition. This is what is called the Schmidt decomposition of a quantum state. So here by quantum state we mean a bipartite state which represents the pure state, like a base state. Okay. Then the Schmidt decomposition says that you can always write this phi as a linear combination of some bases in this way. Okay, some basis means it's not exactly a basis, but some basis elements. Okay, in this way, and this k, this number k, is called a Schmidt number for psi. And then we say this could be a criteria for testing whether a pure state, a bipartite pure state, is entangled or not. And we say that a state is entangled, pure state is entangled, if and only if the Schmidt rank is 1. I mean, is bigger than 1, right? If it is 1, then it is separable. So a state is separable, entangled, if and only if this k is not equal to 1. And I gave you a proof where we have seen that these basis elements, they will come from the eigenstates of the reduced density matrix of the density matrix corresponding to the pure state psi. So this is basically what we discussed, but the main point here was just to show you an application of, or the importance of the reduced density matrix. By the way, if you forgot, I'll just again repeat it because today also it will play a big role in my lecture. So I'll just write it down. What is the meaning of partial trace, which defines the reduced density matrix? So I say, so given a density matrix, or let's say given a density matrix corresponding to this, okay, I defined its partial trace. Let's say with respect to the second system, which we denoted as rho 1, was this. Rho is considered as this. It could be anything, any density matrix. So let us say it is the density corresponding to the pure state, because this is what we used only. And then this is k, and this is, so this k is from this system 2. So there are 2 systems here, let's say. Okay. And this is system 1, this is system. The second system, this is the first system, the second system. And here this k is the basis. Okay. So you are taking the trace. But I also said this is not exactly meaningful because the dimension of k is just the dimension of, so k, if I write k, the state k, this is in, let's say, H2, which corresponds to the state space of the second system. But the rho is the density matrix of the entire system. So let's say if the dimension of this is d2, then it is in c to the power d2. But rho is c to the power d1 times d1. So this is not exactly meaningful, but we said like physicists like to write this way. And there is also a meaning to this. But for me, what I said is that the meaning of this is essentially this, that you take identity and then you apply this k, and then whatever rho is, and then I, and then this k. And the I1 means, I1 is the identity matrix. It's the identity matrix in c to the power d1 times d1. So it is the identity matrix which has dimension d1. That means it's corresponding to the first system. And this k corresponds to the second system. But I have a question to the physics students. This notation is very, very handy. Okay? But it also has a meaning which I did not discuss. I said physicists write this, but by this they mean this. This is mathematically correct. This is not mathematically correct, but this is a useful notation. Okay. Now, can anybody tell me what is going on here? If you write this way, what actually it means? Mathematically, it means this one. But in terms of physics, it means also something. It is not well defined, but it means something. This is a homework for you, for the physics student. What you have to do is, you just consider any matrix rho. You can consider rho to be a 4x4 matrix. So let's say you have two systems, which is a 2-qubit system. It's a bipartite system formed by 2 qubits. So then this has dimension 2. It's 2x2 identity matrix. This is a 2-dimensional vector. So multiply and then see what is happening. Then you will see, and take any matrix rho, which is a density. Any matrix you can take, need not be a density matrix. So once you do this, whatever you find, then try to observe that same matrix, like after computing whatever you are getting, the same matrix in terms of a notation like this. Then you will understand why they denote it this way. It has a meaning. It is not that it does not have a meaning. It has a meaning. It means something. But that can be assessed only when you write this entire thing, and then you'll see why do they write this way. Although mathematically it's not correct. Okay, so this was the meaning of partial trace. So trace over the second system. Similarly, we define, like we can also talk about partial trace with respect to the first system, and that we denoted by rho 2 is equal to trace of 1 and then psi. Okay, so this was the definition. I just wanted to recall, because today also I'll be using this. I just wanted to recall